Hello students. So this is the functional block diagram of 8086 processor in minimum mode. So we have already discussed in the last video uh, how this address and data bus is demultiplexed with the help of ALE. Now let's see the rest of the signals. So here we have like S3 to S6 and S7. These are the status lines which are also multiplexed with address lines. So the status lines S7, which is always high, S6 is always 0, and S5 is equal to interrupt flag. This is as same as that of interrupt flag. If it is interrupt flag is set, this will be equal to 1, otherwise 0. Then S4 and S3, these two status pins gives which segment is presently used. Like if it is 0 0, in that particular instruction it is the extra segment which is used, and 0 1 it is tag segment, for 1 0 it is code segment or no segment, and 1 1 it is the data segment. Okay, so this is about the status signals. Then bus high enable bar, BHE bar, one more signal is there, bus high enable bar. So this signal will be low, this pin will be low when the high order data bus, that is D8 to D15. Okay, so this is to enable this high order, this is used to, this pin is used to enable the high order data bus. If there is a data present on these lines D8 to D15, then this is enabled, that is it is made low. Okay, that particular instruction, like if it is only a byte transfer from the low order data bus, then there is no need of this, there is no data on these pins. This indicates that there is data on these pins. To enable this high order data bus, this pin is used. We'll see clearly, you will understand when we study the memory organization, memory bank system. Okay, then we have a clock signal. Okay, clock. So here the clock given to 8086 processor is 5 megahertz clock, we say, and clock is very important input to the processor to work. Without this the processor will not work. All the activities of the 8086 are synchronized with the help of this clock. So this clock is generated or given to the processor with the help of a clock generator IC 8284A. This is the IC which generates the clock required by 8086 processor. This clock generator is given with a crystal oscillator, connected with a crystal oscillator. This oscillator frequency is converted to the frequency required by 8086 processor, that is 33% duty cycle clock pulse is generated by this clock generator and given to 8086. Okay, and there are two pins, ready and reset, which are given to 8086 from this 8284. Here ready signal, this comes from the IO devices. So when they are ready to transfer, like IO devices, they may be slower than the processor. So when they are ready to transfer the data, they will send a ready signal on this particular pin. If the ready signal is low, if they are not ready, then wait states are to be, because processor has to wait for the data. Okay, so wait states are included in the bus cycle. So that we'll see clearly in discuss clearly when we study those timing diagrams. Okay, so when they are ready, they send a signal on this particular pin, and this is synchronized with the clock and sent to the processor by the clock generator. This is reset pin, the system reset. So this is a switch. When we press this switch for at least, if this particular pin is low for at least 4 clock cycles, then the system is reset. Okay, so this is also synchronized with the clock and given to the processor. And if this pin is high, here it is low but here it is high. Okay, this is high for 4 clock pulses, then 8086 is reset. This processor is reset. So what happens on reset is all the registers internal to the processor are loaded with FFFFH. Okay, and instruction pointer register is loaded with 4 zeros in hexadecimal. So what will be the next instruction that it executes, processor executes, that is from this particular physical address FF0H. This is the 20-bit physical address from where the processor starts execution. Okay, so this location usually it will be in the ROM, because in ROM there will be a jump instruction where a system boot file program is present. So on reset, this particular program which is present at that particular location is executed to reboot the system. Okay, and ready for the further processing. Then we have hold and hold acknowledgement. These when IO devices want a direct memory access, then they can send a hold request for the system bus to the processor. Like if you see this block diagram, you can see the process is like when IO device wants to read some data from memory, or there some file is to be sent to the memory, then it can be like processor is doing the process. It'll read byte by byte from memory and send it to IO device. Okay, instead of that, the DMA, direct memory access controller, it can take the system bus and do the process directly. It can access the memory directly so that it will be faster, and in that time processor can do some other work, internal execution work also it can do. Okay, so direct memory access when requires this system bus for such direct transfers, then it sends and request to the processor on hold pin. So this is to ask the processor for the system bus for direct memory access. So when the processor is ready to give the system bus to the DMA controller, then it sends an acknowledgement on this particular signal and it gives the system bus to DMA controller. Okay, so now this system bus is in high impedance state or tri-state. Okay, then we have interrupt request, interrupt acknowledgement, and non-maskable interrupt. These three are interrupt pins. You know what is an interrupt? So if we are reading a book and someone calls you, that is an interrupt to you. In the same way, when processor is performing or executing some program, and there is a request from a IO device, that is an interrupt to the processor. Okay, so this comes from the IO devices to the processor when they require the processor time, or they want the processor to execute a particular program. Okay, then there will be a request on this particular signal pin. This is maskable interrupt. That means this can be enabled or disabled with the help of interrupt flag. If interrupt flag is set, then only processor will accept the interrupt request on this pin. If interrupt flag is reset, it will not read this pin. So when there is an interrupt and processor is ready to service that particular interrupt, then it sends an acknowledgement on this particular pin. And this is non-maskable interrupt. That means it cannot be masked, it cannot be disabled. Always if there is an interrupt on this particular pin, the processor has to attend this service routine. That means it should stop the present execution, and from the next cycle onwards it has to execute the program related to this particular interrupt. Okay, so emergency services or emergency service routines which are to be executed compulsorily, like so such interrupts are connected to this NMI pin. Okay, this is about interrupt pins. Then we have test bar. This pin is not used in minimum mode configuration. This pin is used when a coprocessor is present in the system. It is used in the maximum mode, so we'll discuss there.